Section 6.3 is binomial radical expressions. I can add and subtract radical expressions. Big idea for this section: like radicals can be combined using properties of real numbers. If we look at the take note on page 374, it says, use the distributive property to add or subtract like radicals. The idea here is that as long as our indexes and our radicands are the same, which means this number is our index and whatever's in here is our radicand, as long as those are exactly the same, we can add or subtract the numbers in front, just like we did with the coefficients on our variables. So just like we couldn't add x and y because they're not the same variables, and we can't add x and x squared, same idea here. We need our index and our radicands to be the same. If we had 2xy plus 4xy, we can add them once our variables are the same by keeping our variables and adding our number parts, and we're going to do the same thing with like radicals here. So in example 1, adding and subtracting radical expressions here, the simplified form of each expression. If we look, here our index is 2 on both of these. They're square roots, so that part matches, and our radicands are both 5x. So since my radicands and my indexes are the same, I have like radicals. And I can take those radicals out, factor it out, and write it as the square root of 5x. Now I can take my 3 minus 2 and get just 1. So simplified here, I have just the square root of 5x. If I look at b here, they're both square roots, but my radicands are different. 7 does not equal 5, so this cannot be simplified. Again here, my radicands are the same, 7xy, but my index is different in each radical. So 3 does not equal 5. Since I don't have the same index, I don't have like radicals, and this one cannot be simplified either. Okay, feel free to pause here and give this a try if you'd like. Now, what is the simplified form of each expression? If I look, I have an index of 3 here and an index of 2 here. Since 3 does not equal 2, they're not the same radical, and they cannot be simplified. It's like if we have an x and an x squared. We cannot put them together. For b, my indexes are both 2, square roots, and my radicands are both x, y. So, since my radicals are exactly the same, I can combine these radicals. The square root of x, y stays the same, and I can take 3x plus 4x and get 7x. For c here, same idea. We have 5 and 5 for our index, perfect. 3x squared and 3x squared for our radicand. So, because our radicals are exactly the same, I can factor those out and take my numbers 17 minus 15 and get 2. In example 2, we are going to use radical expressions here. In the stained glass window design on page 375, the side of each small square is 5 inches. Find the perimeter of the window to the nearest tenth of an inch. So what they're telling us here is each side of the square is 5 inches. 5 inches. 5 inches. 5 inches. And that's helpful because that also tells us then that this is a right angle. And anytime we have a right angle, we can find the length of our hypotenuse. So right now, we have a triangle, right triangle, 5 inches, 5 inches, and we're looking for our hypotenuse. In order to find that, we're going to use Pythagorean's theorem. A squared plus b squared equals c squared. 5 squared plus 5 squared equals c squared. We get 25 plus 25 equals c squared. 50 equals c squared. To get rid of our square, we're going to take the square root. So c equals the square root of 50. We don't do plus or minus here, guys, because we're talking about a distance. Can't have a negative distance. I'm going to reduce this. 5 times 10, which is 5 times 2. Because I'm taking the square root, I need a group of two things. So I can take my 5 out. I only have 1, 2, so that stays inside. So the length of one of these sides, right here, is 5 square roots of 2. And we want to know, find the perimeter of the window. Perimeter, our formula, is 2L plus 2W. If you forget that, guys, think about our rectangle. We have a length and a length and a width and a width. So we need to know what our length is and what our width is. Well, our length isn't just 5 square roots of 2. This is 5 square roots of 2. This is 5 square roots of 2. And this is 5 square roots of 2. So we have 3 edges, or 3 diagonals there, times each one of them is 5 square roots of 2, which gives me 15 square roots of 2. On my width, I have 1 here and 1 here. So I have 2 of those diagonals times how long the diagonals are, which gives me 10 square roots of 2. Now, I can substitute that into my formula. Length goes in for my length, and width goes in for my width. Perimeter equals 2 times 15 square roots of 2 plus 2 times 10 square roots of 2. Gives me 30 square roots of 2 when I multiply my number parts there. I can add those up since I have the exact same index, square roots, same radicands, 2, and my perimeter is going to be 50 square roots of 2. That's not super helpful. Here it says to give us our answer to the nearest tenth of an inch, because if we walked into a place to get like trim for this window, for example, or a frame, 50 square roots of 2 wouldn't be all that helpful. So we can type that in our calculator and we get approximately 70.7 inches to the nearest tenth. Same idea here, except the perimeter of the window is based off our sides being 6 inches. So each side of our square is going to be 6. Okay, side of every square is going to be 6. So to find our hypotenuse here, I'm going to take a squared plus b squared equals c squared. 36 plus 36, c squared. 72 equals c squared. To get rid of the square, we take the square root. 72 I can break down into 6 and 12, which is 2 times 3, which is 4 times 3, which is 2 times 2. So I have 2 times 2 times 2 times 3 times 3. Again, it's a square root, so we're looking for groups of 2. I have a group of 3s and a group of 2s. And I'm left with a 2, so that goes inside. And 6 square root of 2 is my c value, my diagonal. So this is 6 square root of 2. Again, perimeter is 2L's plus 2W. My length, I have 1, 2, 3, times each one of those is 6 square roots of 2. My width, I have 1, 2, times each one of those is 6 square root of 2. Here I have 18 square root of 2 and 12 square root of 2. And now that I know those values, I can substitute them into my equation for length and for width. Perimeter is 2 times my length, 18 square root of 2, plus 2 times my width, 12 square root of 2. We get 36 square root of 2 plus 24 square root of 2. When we add up our like terms, because they have the same index and the same radicands, we get 60 square root of 2. I can reduce that to give our answer to the nearest tenth to be 84.9 inches. And there we just type that in our calculator. A couple things here, guys. The diagonal of a 45, 45, 90 triangle. What that means, guys, is that our side lengths are the same. An isosceles triangle, this angle is 45 and this one is 45, is always our side length times the square root of 2. So whatever our side length is, on the last one it was 5, and we did get 5 square root of 2 when we used Pythagorean theorem. Here it's 6, and we got 6 square roots of 2. And we got the same thing with Pythagorean theorem. So if you recognize that right away, we can go with that. The other thing we could do, guys, here, instead of using our perimeter formula, if we really wanted to, is we could just count up how many of those sides we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we could have taken 10 sides times, if we recognized this, our side length is 6, 6 square root of 2, and gotten 60 square root of 2. So that would have worked as well. In example 3 here, guys, at first glance, it doesn't look like we'll be able to combine these. We have a square root, square root, square root perfect, but our radicands are different. So we're going to try and reduce these and see if, once they're simplified, if we can combine them. So 3 is my smallest one, and it's already simplified. And that's a little bit of a clue to at least look to see if 3 goes into the rest of these. It's not always guaranteed, but if we can break out a 3 from there, here we got a perfect square with 4 and a perfect square with 25. Again, that doesn't always have to work, but if we break them down to our prime factors and take out our groups, that will. So here I have a group of 2's, and I'm left with the square root of 3. Here I have a group of 5's, and I'm left with square root of 3. And here I just have square root of 3. I have a square root of 3, and a square root of 3, and a square root of 3. So I keep my square root of 3, and I can take 2 plus 5 minus 1. 7 minus 1 is 6. Square root of 3. So again, even though they looked different to start with, once we simplified them down, they were like radicals and we can combine them. Again, not always going to work, but at least it's a place to start. So here, 16, I'm going to always start with my smallest one. It gives me a little bit of an idea on how to break things down. Okay, 4 times 4, which is 2 times 2, and 2 times 2. Here, I have a group of 3. I can take that out because I have an index of 3. That group comes out, and whatever's left, 1, 2, stays inside. Don't forget your index number there. And that's a minus because of right here. Okay, the other 2 I'm going to break down as well. 54, again, I'm going to have a 2 left, so if I divide 2 and recognize that 27 is a perfect cube, we can stop there, but if we don't, we can keep going. I'm looking for groups of 3 because of my index, and I have 3 3's here. So I can take the 3 out, and I'm left with just my 2 inside. Again, there's a 2 left in those, so let's try that. If you recognize that 125 is a perfect cube, we can take the 5 out then, but if not, keep reducing until everything is prime. We're looking for groups of 3. I have 3 5's here, so I can take out the 5. The 2 is left. Now, since I have like radicals, I can go ahead and combine those. 5 plus 3 minus 2, 8 minus 2 is 6, and I keep my radical exactly as it's written. So even though in the beginning with the cube root of 250 and the cube root of 54 and the cube root of 16, it didn't look like we were going to be able to simplify that at all, once we simplified each expression, we could combine some of those. And again, it won't always work where you can combine them all. Sometimes even once we simplify them, we won't be able to. But to get it simplified, we have to break down those radicals anyway. And so once we do that, sometimes we'll be able to combine them. And that's what I have for the first half of section 6.3.